Assalamualaikum. Ladies and gentlemen, thank you very much for having me here. Before I start my presentation, I want to start to have a couple of things to say. One of them is a disclaimer. I'm not an AI expert. I'm a trained mathematician and a scientist. So a lot of my works is around in the area of science and mathematics. The other things which I want to say is that I have to apologize before I get started with my presentation. My PA has said that my slides and my presentation is a bit too scientific. And for this conference, most of the discussions is about inspirations, CEOs, talks, and so forth. So bear with me in my presentation, and I try to go as smoothly as possible. Now, I come from a small little island called Singapore, which is one of the most modern cities on this planet. One of the things that you have done is that in this city itself, the government has planned for many years in designing the city to be a smart city. It has started to do autonomous vehicles, smart logistics, smart hospitals, and all sorts of interesting things. Now, even though the city has been designed to be as smart as possible, there's one thing that it cannot able to take care of. That is the weather. If you could see over Singapore, Singapore is one of the highest density of thunderstorms. We have floods. Even the cities have over 20 years planned for huge infrastructure to solve the particular problems. You still have floods and so forth. Now, the climate change is due to a couple of things. One of the things is that it is advocated that this age is considered as an essential threat to modern humanity. And why is it changing? And basically it's because of a very simple thing. It's energy budget. The Earth is taking in more energy than it can dissipate. And basically because is that it has all these emission of gas that actually trap all this energy inside this planet. Now, for over thousands of years, I would say that over the 100,000 of years, we see through a series of IH events. And it stabilized about 10,000 years ago. And this is called the Holocene period. Now, this Holocene period allowed the human beings to actually have agriculture, to have many other things, and so forth. We survived, and we actually evolved over the 10,000 years. However, recently, our weather have changed tremendously. And this CHG effect is going to see an end of this period. We're going to change tremendously and so forth. Now, what you see over here is a simulation of what is going to happen. The heat that is going to be, that you see for the next possible 50 years or so. And the place that, like India, Saudi Arabia, and many parts of the world is sometimes of getting warmer and so forth. Now, one of the things is that the IPCC or the climate folks have actually, in fact, do a lot of simulation. 1 or 2 degrees may sound not too much, but it's important to note that in a global average, 1 or 2 degrees is a lot, because in some places, you will have temperature of increase of 7 degrees to 10 degrees, and so forth. Now, that is only about 1 to 2 degrees. What if the temperatures actually go up to 4 degrees? Then that would be a catastrophic. The other things is that what it will cause is that you will see sea level rises because of global warming. Arctic ice is going to melt, and so forth. Water is going to rise, and country like in Singapore, which is only a couple of meters above sea level, is going to be a threat. And so one of the things is that the government would have to find ways to actually prevent the water from coming into the city. So what you're going to do is you're going to see extremes. There will be more areas that is going to be hot. There's more areas going to be more wetter, like Singapore whatsoever, a lot of rains. And there are certain areas it's going to be extremely dry. So you're going to see more and more of this extreme weather. Now, what would be the climate risk be? Of course, like I said, a warmer planet is going to be highly agenetic. For those who have done chemistry or physics, you know that when you have a boiling water, there is a lot of activities going inside a warm water. So this is the same. The planet is a fluid dynamics problem. So you're going to see a lot of extreme weather, more fire, more storms, and so forth. One of the things is that we see recently is that the California fires in about 2019, the Bangkok flooding, and Australia wildfire, which have caused a lot of wildlife, and including properties and so forth. This extreme weather frequency is not just the extreme weather, it's also the frequency. We're going to see more and more of this in the near future. Basically, events that happens every 20 years, right now it's happened almost every 2 years, or some of them even every year. So we can see more flooding. And the cost is, of course, is tremendous. So we are in the US itself, about $100 million worth of damage is in 2021. So in 2025, you see that there's more of this. Climate is changing, and you will see that there is lower precipitation in the Mediterranean. That is what being predicted. The decrease of ice and snow and causing flooding, right? Heat increase, sea level rises, and so forth. There are also things like disease. Don't think of it as just that because of heat itself. The heat is going to allow the mosquito to actually multiply. So you're going to see more dengue fevers, more other things. You can see also that the ice is melting in the Arctic tremendously. There is evidential events showing all these things as happening. So we are seeing the water rises. For example, already in Bangkok, sea levels already rise tremendously, and you will see more floods. The city is actually sinking. One of the things is that the AMCO, and don't worry about too much, and this is what we call Atlantic Barabodian overtuning circulation, that is going to cause, going to be weakened. Of course, it's not going to die away, because if it die away, then what we have is that, if you remember the movie, it's called The Day After Tomorrow, that will happen. But it's definitely is going to be weakened because of greenhouse effect. Now, I'm going to switch topic a little bit, and we take a look at the state of the art of AI algorithms. Now, many of you who have already done AIs, and you've seen a lot in the show itself, AIs is everywhere. One of the earliest success of AI is into computer vision. Now, computer vision is mature enough to be actually implemented. It's no more just stay in the lab. You see that it can be applied into car counting, people recognitions, using in medical images, and so forth. The other thing that is growing very fast is natural language processing. And for those of you who don't understand what is natural language processing, it basically is to able to analyze languages, natural languages, like English, Chinese, Koreans, or so forth. Yes, a lot of new technologies coming out. They're getting bigger and bigger. GPT-3 is about 175 billion parameters. Megatrons with 500 billion parameters. And then the Wutao in China is about 1.75 billion parameters. This allows us to actually build a lot of new technology and applications. Conventional AI right now is seen everywhere. You took out your handphone, you have Siri, Google. You have, when you use AWS, you have Amazon's Echo, and so forth. In cars itself, now some of the cars have car assistants. So these technologies is become very prevalent. But what is interesting over here is that the GPT-3 and perhaps even GPT-4 is that it has give you a hint of cognitive thinking. Because in GPT-3 right now, there was a test that shows that GPT-3 is able to write a short paragraph, and maybe in the future we're able to write entire articles or even a book. So the artificial intelligence of GPT-3 now have shown us that there is give us some hints on how cognitive thinking works. This is examples of how GPT-3 not just in languages, but in programming. Using natural language over here, you type in just in natural language, you can actually generate out codes, computer codes. So what does it mean? It means that in the future, if you bring that forward, developers is going to have an easier life because now you will have codes that automatically correct itself, just like some of your word are correcting sentences. You are able to write codes. In fact, you're able to generate codes. Another thing is going to be changing is that these technologies then allow us to actually AI to create AI. What it means is that now you can think of ways of using this to ask the artificial intelligence itself to create another artificial intelligence. And then you can create another artificial intelligence, and so forth. So you could see over here, this is a very good example on how GPT-3 can be used. Of course, the Chinese is also very relentless in their research. They call it the Wutao 2.0. This is one of the world's largest language models on this planet. And if you look at, for those who understand Chinese, the words over there are actually poems. One of the most difficult things to do in a Chinese language is to actually write a poem against another poem. In the olden days, where scholars actually go for imperial examinations, they have to write poems in order to pass the examination based on certain themes and topics. And this Wutao 2 is able to do that. I mean, of course, it has also, against many other benchmarks, it has beat many other language models. Many of you would have seen about AlphaGo, and you will know about the stories. AlphaGo beat Mr. Lee in 4-1. But what is important over here is that AlphaGo is based on a very simple old idea called reinforcement learning. And reinforcement learning, like the earlier speaker has talked about, is about learning how to do things. Reinforcement learning basically means that it has a penalty or whatsoever. Do not worry about the equation that you've seen, but what the whole idea is that it has penalty and rewards. If you do something is right, you get reward. If you do something is wrong, you get a penalty. And that's how the algorithms learn. And these algorithms actually drive these algorithms in AlphaGo. Now, AlphaGo 0 is even more impressive, right? What it does is that now the Go game itself is played against itself. It creates AlphaGo or its own version, and then it plays against itself. So think of it is now computers is able to learn from itself rather than learning from a human being. That actually translates to a lot of game companies, a lot of reinforcement using games as a way to actually train their algorithms. What you see over here is that, again, it allows us to learn about some of these, what is intelligence is about. Do we have understandings of what intelligence is? Reinforcement learning, on the practical side, it applies into many things. One of the very important things is the robotics. Things will be like the autonomous vehicles and so forth. I'm going to show you examples over here. This is a robot that the user do not program the robots to do to do what it's supposed to do all the tasks. What the programmer has done was they asked the robots to put the red plug into the hole into the red hole, into the hole, right? And so the robots will actually try and error until it managed to put the red pin into the hole. And this is what reinforcement is about. So going into the future, you could see that more and more of these robots is able to learn by itself. So AI transforms in every industry sectors. You see that everywhere. You see on the floor, there's a lot of new technologies, new companies being formed, new startups, and so forth. And that's one of the reasons why companies like Facebook's, Google's invested huge infrastructure to do their AI training. This is one of the world, this is just announced, world's largest AI supercomputer, which consists of 4,000 plus GPU. So how do we apply into Earth science? Now, as I mentioned before, the Earth science itself, there is many things that be done. One of them is to predict the weather, predict the climate, to understand the satellite image that you receive, all the different images, the data from many different sensors. The other one of the things is that you guys may know that to simulate the Earth take a very long time. You need a very powerful supercomputers. One of the things is that how can we actually use AI to actually cut down the amount of computational time that is required to do that simulation. So these are all the different examples. That is how AI is being used in the use of climate modeling. One of them is that how do you accelerate physics parameterizations in using for mid-range weather forecastings, rapid intensity, and other things. In fact, one of the very interesting things is that in the climate models, some of the data are actually missing. We could actually use machine learning to actually generate out the data. And I'm going to talk about it a bit more later. So in the US, NOAA has set up a centers basically for artificial intelligence, looking at ways of using artificial intelligence to solve climate modeling problems. There are other climate-related technology that is need to be solved. Now, we do know that one of the things is that we want to go greener. The solar energy is abundant. In Saudi Arabia, in the Middle East, you have a lot of sun. How do we enhance it? We all know that we all build solar farms to actually convert those solar energies into electricity. Saudi itself have built a huge solar farm which is able to generate out 300 megawatts of power. In China, Morocco, and many countries where have huge deserts, they could actually put in all these solar panels. But doing these solar panels has multiple problems. One of them is that at the moment right now, solar panels is still not very efficient. We need to get new materials. The other thing is actually storage. All this energy that's been generated out has to go into some form of storage, or it has to be distributed one way or another. So battery technology has to be improved, solar panels technologies have to be improved, and this actual fact is material science research. So one of the things is that the AI is being used now for material science research. Now, material science research, for those of you who have done material science research, will know that doing material science research takes a very long time and it's very expensive. Simulation helps, but it still takes quite a fair bit of time. So what you have right now is that we have used new ideas, making use, remember the technology that used for deep fake, that able to generate out fake characters and so on. That technology is based on what we call gangs, and that technology can be used to generate out all the different possibility of materials that can be used to solve a particular problems. So these ideas is now being used in many of these material research. So it can be help to solve some of these solar power panels design and also for battery design. The other thing is fusion energy. Now, fusion energy is a very nice idea because it is clean, there is no nuclear waste. However, it is almost uncontrollable, right? So one of the things that many big countries is now doing is to start wanting to build this generator. To build this generator is extremely challenging because if you look at it, the turbulence inside there, the plasma turbulence inside there is very violent. You're going to heat this up to thousands of degrees, almost equivalent to the temperatures in the sun. So it's very violent, but you have to find a way of controlling it. One of the ways to controlling it is use some form of magnetic structures to control this turbulence magnetic plasma. So because of the complexity of it, Professor Tang, who is a good friend of mine, have developed a way of predicting the instability, and it is able to control this plasma. So these algorithms right now is being used in the Tomahawk experiment to do control of the generator. Wind power itself, as we know, is using the winds, which is a fluid dynamic problems. Now, many of you, or those of you who have in the wind design area, will know that designing a wind farm is very expensive, and sometimes maintenance is an issue. So we need to actually study it. Now, studying how the wind flows across the turbine is a challenging thing. So, and this is the only equation I'm going to show, and this basically is set of a form of a Navier-Stokes equation. Now, one of the things is that using AI, or rather what we call a physics, is a new form of artificial intelligence neural network. It's called the physics-informed neural network. We combine physics and neural networks together. That's allowed ones to actually, in fact, then able to simulate that in a very, very quick time. The other things that is very important in the climate change is the design of carbon capture and storage process. Now, the whole idea is to capture the CO2 from bioenergy combustion, the biofuel production, fossil fuels, and so forth, and then able to send it down right into the ground to actually store it underground. Now, this is basically a very complex complex engineering problem, because one of the things is that when you pump this CO2 into the ground, there is a mix of fluids between waters and gas and so forth, and it's a complex models. We have developed the mathematical models to actually understand it, but to simulate it, to understand how it actually works, takes a lot of computational power, and we do not have the time. So one of the things that my colleagues have done in MV research is they came out with an artificial intelligence architecture called the Fourier neural operator. Again, this is an operator that's able to solve the partial differential equations in a very quick time that allowed them to simulate the different scenarios that needed for this carbon capture and storage. So the scientific challenge, there's still a lot of scientific challenge. Data labyrinth, limited data, and so forth, and the list goes on and on and on. We need actually people like yourself, universities, to help us to actually solve this thing. So one of the NVIDIA challenges is that we want to able to solve all these things in a very quick time. Not by brute force, because the semiconductors is not able to deliver the supercomputers that needed to actually simulate the planet Earth. What we want to do is to able to simulate the planet Earth up to 1 kilometer small, which means that you need almost almost a million times the size of the supercomputer right now in order for us to do that simulation. And that is not possible because semiconductors can only do, if you go at Moore's law, 1.8 times every 2 years, and so forth. We have to look at new algorithms. Artificial intelligence seems to be a promising way to move forward because we see that, for example, the Fourier neural net operators, the new neural networks, the physics-informed neural networks, and so forth, help us to do that. So we are developing a suite of software stacks called Nvidia Modelers that's able to solve these things, that integrates together with our GPUs and so forth. Together with it, we want to be able to visualize it. So from data, satellites, oceans, the ecosystems goes into a artificial intelligence neural network simulator, and then goes into one of the big supercomputers, and so that we can predict wind energy forecasting, extreme weather predictions, and disaster mitigations, and so forth. So with that, what we have done is that we have done this.
High-resolution weather simulations, as provided by DKRZ's ICON code and vast amounts of observational data, allows us to determine the state of the Earth with unprecedented fidelity. But exploring and working with this data can be a challenge. Technologies like the Nvidia Omniverse Peer Review Connector allows scientists to interactively analyze weather and climate data in 3D, to combine information from multiple sources, and to explore what-if scenarios. This takes us ever closer to a realistic, interactive digital twin of the Earth. Let's look at two examples. In August 2019, Hurricane Dorian developed into a massive Category 5 hurricane, causing over $5 billion in damage in the Bahamas and the southeastern US, with sustained winds of 185 miles per hour. Viewing high-resolution simulations like these integrated forecasting system simulations in Omniverse allows scientists to analyze the behavior of storms such as this in detail, interactively, and in full 3D. This not only aids in understanding the physics of weather systems, but also allows inaccuracies in models to be identified and refined. With the Omniverse Peer Review Connector, visualization modalities of peer review, like streamlines, become available within Omniverse and can leverage the RTX renderer or be fused with data from other sources. These sources can be static or computed on demand, such as mapping service, surrogate model, or an AI-informed physical model. Here we show AI-based image segmentation of satellite data, which was used to detect flooded areas and to classify land use before and after Dorian hit. The network performing the segmentation can run as a service and be triggered on demand. Once we have interactive access to all this Earth science data, a next step is to play through different scenarios. On-demand evaluation of surrogate models or access to real-time physics engines can help exploring the impact of our actions in this virtual world. With access to real-time physics models as enabled by Omniverse, we can not only explore pre-computed data, but also simulate on the fly. Here, we use real-time fluid dynamics simulation to show the vapor plume emerging from a cooling tower. A user can quickly explore the impact of the plume, depending on the wind conditions or the steam output. Similar models can be used to interactively explore the dispersion of aerosols or contaminants. Nvidia Omniverse is a powerful platform for massive-scale digital twin simulation. We're excited to see where it takes us next.
So this is the technology that Nvidia has built that we want to help solve the problem. And not only that, we are setting up research centers all over the world in collaborations with the universities to solve some of these problems for smart cities, climate change, and so forth. At the moment right now, I run the AI technology centers. We have about 17 centers across the world and in 12 different countries. And I'm looking forward to actually have some collaborations with some of the local research institutes, universities, or people or companies who are interested in doing weather research and many other things. So with that, I thank you very much.